My name is Paul Corcoran. I'm with Wolf & Company. We're a 112-year-old CPA firm offering audit, tax, and IT assurance services with a focus on healthcare, HIPAA security and privacy assessments, high trust certification, pen testing, social engineering, and a lot more. Welcome to our next session today titled Predictive Model Evaluation and Deployment in Production, presented by Sayon Dutta. Sayon is an assistant professor of emergency medicine at Massachusetts General Hospital who serves as the physician lead for emergency medicine and clinical decision support at Mass General Brigham Digital. He completed training in emergency medicine at the Harvard-affiliated Emergency Medicine Residency and then joined as a research fellow at MGH, during which time he earned an MPH in quantitative methods at the Harvard School of Public Health. Please join me in welcoming Sayon.
What's up, everybody? How are you? Good morning. All right. So my name is Sayon. I'm the physician lead for what we call at Mass General Brigham the Clinical Decision Support Team. It's part of a larger team that we call the Clinical Informatics Team, which is part of MGB Digital, and we're essentially the group, the team that runs and manages and maintains and builds stuff in Epic, which is what we have. I don't think that's a surprise to anybody. All right, so we're going to talk about predictive model governance. I unfortunately have no financial disclosures, but feel free to hit me up if you want to give me some money. All right, so Mass General Brigham comes from Mass General Hospital and Brigham and Women's Hospital. I don't think that's a surprise to anyone either. We have a lot of hospitals, we have a lot of patients, we have a lot of physicians. I think we're the largest employer in the state, but I could be wrong. And so that's just a background on us. So what are we going to cover today? So first we're going to cover predictive models, or machine learning, or artificial intelligence is kind of everywhere, and it's a really hot topic in medicine right now. We're going to talk about that and the kind of the difference I see between the hype and the reality of what's been going on. We're going to talk about why governance of machine learning and predictive models in medicine is kind of crucially and critically important. We're going to talk about how to measure performance of these machine learning models, because there's going to be a lot of people that come to you and say, we have this thing and it works really well and we want you to buy it, right? And I'm going to kind of walk through what you kind of need to do on your own to a certain extent to prove whether it's worth it or not. We're going to talk about what you do after a machine learning model is in production and what you need to do to make sure that it continues to perform the way that you think it should. And then finally, we're going to talk about measuring the impact of machine learning, right? All right, so in terms of machine learning and predictive analytics in the field of healthcare, there are a lot of models, right? This is a little joke here. But there are, especially around COVID, there have been hundreds, probably even thousands of papers that have been published about, we're going to predict if someone dies from COVID, or we're going to predict if someone's on oxygen if they have COVID. I'm guilty of this myself, right? This is just what happened because people didn't understand the disease very well. They have big data sets. Pretty much everyone now is on electronic health records. It's just like kind of a prerequisite to doing machine learning, right? You need data that you can pull from the system to be able to train these models. But almost no models that have been out there for COVID specifically, or even really anything outside of COVID, has really made a huge impact in medicine, right? And that might be a hot take to some people. Some vendors might disagree. But there have been very few studies that have shown we put this model into place, this clinical outcome, this impact improved so much, right? It's very rare. Usually what people do is they get this big data set, they churn all this data around, they figure out a machine learning model, they try 30 different models, and they come up with something that they think performs the best. And then they write their paper, they pat themselves on the back, the PI goes and buys everyone a drink, right? And then that's it. That's where the project dies, right? And so most published machine learning models are actually very poorly reported. They only report on maybe one outcome metric. They only report on one aspect of model performance, but not all the things that you need to know. And they're at high risk of bias, and we can talk about that in a few minutes here. And so, like I said, so most people that go through this process, they create a data set from their population. They train the machine learning model. They figure out how well it works on the testing data set, which we'll go through. Sometimes they'll try it on another data set from a few months later to see if it still works. Almost nobody does external validation, which is to see if a model works at a different site with a different population. And then beyond that, almost no one beyond that actually puts the model into production. So most things in the medical literature usually just stop at internal validation, and that's it. And that's a problem, right? And so why is that a problem? So the majority of external validation studies of a machine learning model will show that the model performs worse, right? If I train a model at Mass General and I only use Mass General patients, and then I try it at a different hospital in Colorado or Idaho, it's not going to perform as well. And if it performs better, there's probably something wrong, right? Honestly, there's probably something that happened in the code that is wrong that made it perform better at an external site. But most of the time, people don't go to the hassle of doing that because it takes work, right? It takes effort and collaboration and mapping out your data and having the same SQL query off of your database, pull the same kind of features. It's not easy. And even models that are produced by large electronic health records, like Epic, for example, when they train their data sets, when they train their models, they train off of a certain number of sites, right? Not their entire Epic customer base. They might be 2 or 3 hospital systems. And then they make a model. But then when other people go and try that model, which we've done extensively on probably more than a dozen of their Epic models, we usually find that it doesn't perform as well for our population than they said it performed when they trained it, which is not really surprising. It's just patients are different, populations are different, right? Things happen. And on top of that, even if it does perform decently well, it has to perform not only well on its own, but it actually has to perform better than what a physician would do, right? It has to provide additional value beyond what a physician already knows. So if a patient is presenting to you and you think that they have sepsis, and it's clear as day that they have sepsis, they're hypotensive, they're tachycardic, they have a fever, right? Having a predictive model tell you that they have sepsis doesn't add anything, right? It just tells you something that you already know. And so a machine learning model really excels when it can tell you that outcome, not when it's obvious, but when it's not so obvious, and not right before it happens, but hours before it happens. So you have a chance to intervene. Right. All right, so on top of that, machine learning models have shown, over and over again to have algorithmic bias, right? So what does that mean? So it means that essentially that if you are training a model on a certain population, say you're training an image classifier to classify, is this a bride or not, right? If you're only looking at the picture on the left and that's all you have in the training data set, it's going to identify that pretty well, but it's never going to identify the Indian bride on the right? Because it looks so different. They're both brides, but if it's not in the training data set, it's not classified in the training data set as being a bride, it's not going to work, right? And so there have been countless examples of this in the medical literature that have come up over and over again. And it's a hard problem because you need to basically have really large data sets. You have to have diverse data sets. You have to have sometimes oversampling of minority populations in order to overcome this bias. All right, and so here's an example, right? So this is a pretty famous paper out of Science by Ziad Obermeyer, who was a prior resident in our program. And basically, he did an analysis of this widely used proprietary machine learning model that basically looked at how much health expenditure a certain population would have. And what he found was that it basically predicted that black patients needed less health care than white patients, right? But the truth is really, that's not really the truth, right? The reason that it showed that was because less money was spent on black patients than on white patients. And if you actually corrected for how much should have been spent, then the algorithm would have looked a lot different, right? So understanding where your data is coming from, what features are being used, all of that is critically important to understanding if your machine learning model is actually predicting what you want it to predict, or it's just amplifying existing biases that the data might have in general. All right, so finally, like I said, having a good machine learning model is great. Get your paper published, but if it doesn't actually make an impact on a clinical workflow, if it doesn't make patient care safer or more efficient, then it doesn't really matter, right? You can be great at prediction and make no impact, and no one really is going to care in the end, right? And so, people have shown that there's a big difference between making a highly accurate algorithm and having something that's actually successful in making a clinical workflow better. And I think that's the gap that we need to bridge. All right, so why is governance important? All right, so actually, before I keep going, who in here are doctors or nurses? Okay, cool. Administrators and executives. People that have trained a machine learning model before. Nice, okay, cool. All right, so there's a little mix of everyone. So first of all, why is governance important? This is where, this is the main point of the talk. So first of all, you have to understand that, like, if you're making a machine learning model and it's not a problem worth solving, then you're kind of just wasting your time, right? In terms of machine learning governance, it's really important to have the right people at the table, and it's important to understand the overall life cycle of the governance process, the machine learning training and validation process. All right, so the first step in developing machine learning models in healthcare is problem selection and defining the prediction task, right? You have to have something that is worth predicting, that adds value on top of what a physician or a nurse or a caseworker or whatever population you're targeting the model for is focused on. And so I'm just going to pick on this paper, right? Machine learning-based prediction of COVID-19 diagnosis based on symptoms. So they wrote a paper, they got it published in a Nature article, in a Nature journal, and it basically looks at your symptoms and tells you if you're likely to have COVID. So that would have been great in March of 2020, but I can tell you, if you were working in the ED and someone came in March of 2020 and they had cough, fever, and shortness of breath, they had COVID, right? You don't need a machine learning model. This is like pretty obvious to even me, right? So you're gonna get a great AUC score, not really that helpful, right? And if you're in a place that doesn't have COVID testing, they probably don't have the ability to do real-time machine learning modeling anyways, right? So you got a data set, you predicted something that's fairly obvious to everyone, publish your paper, and I'm sure nothing happened afterwards. All right, so anyways, who should be at the table? So I'm going to talk about what Mass General Brigham does in terms of our team and our governance process. Certainly, you need machine learning experts. There are physicians and nurses that are out there that work clinically every day, that interact with your electronic health record, who don't know anything about machine learning, and probably shouldn't, right? Because that's not their job, that's not their focus. But if you're evaluating machine learning model, you have to have someone that's there that understands what a random forest is, or a support vector machine, or a large language model. They have to understand what model performance, how to evaluate it, and what's important, feature selection and engineering, hyperparameter tuning. You need someone that understands what that language is so that they can ask the right questions of the person that's presenting the model and wants you to implement it or wants you to buy it, right? But you also need clinicians. You need doctors and nurses and pharmacists and whoever is impacted by that model to be there, because they're the ones that are going to catch this thing, right? That this is a great model, AUC of 0.9, totally useless clinically, right? You need data analysts that are able to pull data and do analysis on their own in terms of model performance. And you need administrative support, right? Someone has to run the meeting and take minutes and make sure that everyone stays on time, specifically me. All right, so we broke this up, in terms of the roles that we just talked about, we basically have those roles, informaticians, which are clinicians that work on our team, on the clinical informatics team. There's hospitalists, there's someone from outpatient medicine, there's anesthesia, there's myself from emergency medicine, and nursing counterparts. We have data scientists, we have application coordinators, which are essentially developers in our EHR. And we're the ones that essentially will take a model that gets presented to us and do the first evaluation and ask the questions that are fairly standard, like what kind of model is this? How is it working? What variables is it using? Did you try this somewhere else? Has it been externally validated? We ask those questions. And when we feel like they've come up with a satisfactory answer, we take it to our larger governance meeting, which basically has machine learning experts, we have experts in diversity, we have ethicists, we have the CMIOs from our different sites, and enterprise CMIOs. And that meeting, they present the model, they talk about the outcome that's trying to get predicted, and we talk about the model and whether or not it's clinically useful, what kind of workflow it would be. And if it gets approved there, which is our predictive model governance meeting, before we turn it on for users, we always take it to the actual clinical groups that would be impacted. So it might be a primary care group. It might be emergency medicine. We have existing kind of consensus groups that make decisions around our EHR for all of those things. And we take it to them first before we turn it on, right? Because it needs kind of a technical review and it needs a clinical review. All right, so how do we do this in terms of, so we split this up a little bit in terms of how we do things for Epic released models versus models that come to us from vendors or from other researchers. So we have that initial review process, which we just talked about. We have an intake form, which I'll show you. And what we like to do for models that come from our EHR is we just put it into the system. We map it out, we do some validation, make sure that the variables are correct, and then we just let it sit and marinate in the system and run and make predictions. And the number of months we let it sit there depends both on how much bandwidth we have to analyze it, honestly, but mostly like how many predictions does it need to make before we can be confident in the performance analysis that we do next. We do this performance review, which I'm going to spend a lot of time on, and then we take it to our predictive model governance group, because going to them with data on how it works on our population is extraordinarily valuable, right? It's much more meaningful to them to say, this is how the model performed here versus how they say it performed there, right? And then we go to clinical approval with those CCGs I talked about, and then we do production release, and then we do post-live monitoring. And I'll show you a bit of all of that. So if it's a custom model, like a model that I made or someone else has made, or someone that's coming to us as a vendor, we kind of mix things up, and we're flexible in that way, because sometimes it is, we have a few extra steps, right? So first thing we do is because it's harder for us to implement those models directly, we do some of the kind of early technical approvals earlier on. And then we do a formal code review to look for security risks by our IS team. But then we do a silent release, like we said before. Then we do performance review, and then we go to clinical approvals and that kind of thing. So it's a little bit different depending on the type of model. All right, so this is our intake form. We ask a lot of questions on here. There are a lot of technical questions that we ask. But basically, the main point is, what is the model trying to achieve? What features, what variables does it use to come up with that prediction? Have you tried this before? Has the model drifted in terms of its performance? Has this been published? How do we tell if the model is working or not? When should we turn the model off because we now have identified that it's not working or it's broken? We ask a bunch of questions. And it's okay if they don't have the answers to all of them, right? There are going to be things that they just don't know yet, or it's too early. And we're actually okay with groups coming to us and say, we have this problem. We want to be able to predict this. We need your help to build this model. And that's okay too. They're not going to have all this information because they're looking for us to do the modeling part. All right. So this is a screenshot of us having one of these consensus group meetings, these predictive model consensus group meetings. This was a model that looked at radiology reports and tries to predict whether or not a patient is at risk for intimate partner violence, right? This is something that we miss all the time because it's subtle, it's hard to identify a pattern, especially when that kind of thing might have been going on for months or years, right? That's the best picture of me that I could find for this screenshot, although I looked at the whole video. But this is what we do. We ask the creator of the model, which is in this case a radiologist, to come forward and say, this is the model that we created, this is where we've published it, this is the review that we've done, this is the population that's been worked on, and talk us through it. If it's a custom model, we always do a code review. So basically this is primarily for information security. We just want to make sure that there's like nothing in the code that's malicious, that's like, reaching out to Pirate Bay or some crazy thing, right? Usually it's fine, it's not a big deal. And so this is, for example, we use Azure DevOps and we basically commit the model there, and we have like someone who knows how to program and has a lot of Python experience to look at it and make sure it's cool. All right, so they just look at the code, and it usually doesn't take them all that long. All right, so what do we do next? So then, once we know that there's a good use case, we'll just put it into the system, right? So this is, for example, one of the EPIC models that aims to predict if someone is getting admitted to the hospital if they're an ED patient. So we'll just build it out, we'll map out all the variables, and we'll put it into the system. And like I said, we'll just let it marinate for a while. And then after a certain amount of time has passed, the appropriate amount of time to be able to assess whether that model is performed, we do a very extensive evaluation of that model, right? And what questions do we ask? We ask, did it work somewhere else? Does it work here? Is it biased? Is it explainable? And then we get into some of the impact stuff as well. Okay, that's a repeat. So just to go over just very basic machine learning stuff, right? Usually there's a development population where you have a data set, you split that data set randomly, 70% you say for training, and then you hold aside 30% or 20% to test whether the model works. That's usually where people publish their papers and the thing stops, right? An external validation is using a different data set from a different site, a different time period, and then trying the model that's already been trained on that data set. And these are the kinds of things that we look at when we are looking for model performance. So the classic thing that most doctors would recognize is something called the AUC curve, right? The area under the receiver operator curve. And this is just to give you a sense of how the sensitivity of the test, in this case, usually, they either have sepsis or they don't, and the specificity are matched. And so, the curve approaching the top left corner is a really good model, and the ones that are on the dashed lines are basically coin flips, right? And so this is a paper we helped on for a COVID-related model, and they're showing a bunch of different models that they tried and the different ROC curves for that. And on top of that, one of the problems with this kind of metric which is pretty problematic, is that if you have something that's pretty rare, it's a rare outcome, and most of the predictions are low, like predicting they don't have it. Most patients, for example, in the hospital don't die, right? The AUC will be lifted by all of those negative predictions on low-risk patients. So you're gonna get a false sense of reassurance because your AUC is good, and it's because most of your low-risk patients have low scores. That doesn't mean that your moderate-risk patients or your high-risk patients have high scores, but you're getting this like AUC lift on that. So it's really important to actually look at other things. So one of the things you can look at is something called a precision recall curve, right? So this is looking at the positive predictive value, which is, if I say you have it, do you actually end up having it, right? And that is actually probably what doctors care about most of all, right? You're saying this patient has sepsis, do they end up having sepsis or not? And then balancing that with sensitivity, right? Because if you want a really good positive predictive value, for example, and I'll show you this in a second. If you want a really good positive predictive value, you can say, yes, I'm going to wait till the score hits a threshold of 85, right? And then I'm going to warn the provider. You could do that. You'll have great positive predictive value. Your sensitivity is going to be crap, though, right? Because almost no patients are going to get to that score. And so you might only be picking up 4% of cases of sepsis, right? So it's always a balance between the two. All right, the other things that you need to look at are calibration, right? Does the model overall over-predict or under-predict the outcome? And then we go through all of this. There's a bunch of other things that we do as well that I won't go into. But then in the end, you'll get something like this, which is, in essence, a model card, which says, what's the outcome, who was included, who was excluded, what are the features, what's the performance, both on an encounter level and on a prediction level, and then you go through it like that. And this is kind of what we expect when models come to us for governance. Am I on time? Am I over? All right, plenty of time. Okay, good. All right, so we published this paper, I think, last year, and this just kind of goes through what I think, anyways, a solid evaluation of a model would be. So this is, again, the EPIC risk of inpatient admission from the emergency department. And we did this validation with 329,000 encounters across all of the EDs in our site, in our healthcare system. And again, so these are the curves that we want. This is the data that we want. We want to look at the receiver operator curve, which is panel A. That gets you the AUC. In this case, was 0.85. We look at the precision recall curve, which is that balance between positive predictive value and sensitivity. And here, the area under the precision recall curve is 0.64, which is pretty good given that the incidence of admission from our system from the ED was 25%. 25% of patients got admitted to the hospital. And we have an area under the precision recall curve of 0.64, so it's way higher than the incidence, which is good. It's a pretty well calibrated model, and there's pretty good discrimination. So in panel D, it's saying if you have a really low score, you're almost certainly going to get discharged. If you have a higher score, the risk of you getting admitted is higher, but it's not certain, right? All right, and then we basically, on top of that, look at model performance by subgroups, right? So we want to know not just does the model work overall, but does it work for the entire population? So how does it work for patients that are age 18 to 29 compared to patients that are over 90? How, does it work the same for men and women? Does it work the same for different racial groups and ethnic groups? ESI is Emergency Severity Index, right? So it's your triage severity. So the patients that are the sickest, they're coming in as immediate triage severity. Almost all of them get admitted, right? Versus someone that comes in with, a hangnail, they're never going to get admitted, right? So how does the model perform for those different subgroups? And how does it change between an academic center like Mass General and, the 6-bed hospital at Nantucket? Does it work the same way in both of those places? And kind of more importantly than the overall model performance is when in the time course of the encounter does the model make the right prediction? And so, for example, here we're looking at like the time, all those little lines are basically each encounter and the model scores of each encounter over time. You come in and every 15 minutes you're getting a new prediction in terms of what your likelihood of getting admitted. And so usually that peaks around 2 hours or so into an ED visit. But when do bed requests actually get placed? If they're getting placed right afterwards, then you're not really giving anyone any degree of warning, right? And so looking at the lead time is really important. And then on top of that, we look at not only encounter level performance, but we measure the performance of each prediction individually over a horizon, right? So if I'm saying now at 12 p.m. that your risk of getting admitted is high and is true, do they actually get admitted within the next, 1 hour, 2 hours, 4 hours, 6 hours? Because that kind of gives you a sense of how important each prediction is. All right, and so this is what I was getting at before. There's always a balance between positive predictive value and sensitivity. If you want to be very sensitive and catch every possible case of sepsis or every possible case of whatever you're trying to find, your positive predictive value is going to be pretty poor. unless you have an amazing model, right? And so understanding what the threshold should be is really important. I just had a meeting yesterday where we talked about a case of a patient that had a bad outcome, and they were on a non-medical service, and something happened and they deteriorated. And they looked back at our deterioration score, and the deterioration score was like super high, but the resident didn't see the score, they didn't have a view into that, and they didn't escalate the care. And so, of course, they do a root cause analysis, and they say, can you guys fix this for us, right? Because that's a lot easier to say than like, we're gonna train everyone to do the right thing, right? Especially in July, right? So they'll come to you and say, can you fix this problem for us? Can you show an alert when the deterioration index is over a certain amount? And I say, sure. And I show them the graph and I say, where do you want me to show it, right? Do you want me to show it at a number of 50 or 55 or 70? And they're like, well, you tell me. And I'm like, it's your threshold for how sensitive you want to be versus how specific and how much positive predictive value. If you want to catch 80% of cases of deterioration, right, you need a sensitivity of, you need to set your threshold at 20. And at a threshold of 20, your positive predictive value is going to be 45%, right? If you want to be very predictive, but you don't care if you miss a bunch, you can set it at 60 and have great positive predictive value, but your sensitivity is going to be 15%, right? It's always a trade-off every time. And so that is an important thing to understand. This is not like a troponin, right? This is not like all the tests that we're used to ordering in terms of determining this is an NSTEMI or this is not. It's a kind of a different animal, and we have to treat it as such. All right, and so finally, the threshold you set is going to determine what your lead time is going to be, right? If you want to be very predictive, you have to reach a threshold of 70 before we're going to show you anything. You can do that, but the amount of warning you get between when that prediction is made and when the outcome happens is going to be smaller than you say, for example, we're going to show a warning at a score of 20. You're going to get to 20 faster, you're going to have more lead time, but your positive predictive value is going to be lower. So it's all a balance, and it's important to look at this stuff so that you can figure out what the right numbers are. All right, so after we do all of that, we do this big evaluation, we show the data, we present graphs like this when we have the data available, and then we all vote, right? As the clinical consensus group, they get together, they vote, and then after that, we put it in production, right? So this is an epic screenshot that I probably shouldn't be showing you, but this is, it goes into production, and then afterwards, what really is important is a couple things, right? One thing is that you have to make sure that the model continues to perform, because there is model drift, and I'm going to give you some examples of that. Things change in the system, build changes are constant, right? And some of the things that some other team is going to do or we do to ourselves is going to break the model. And so you have to understand that and look out for it, and you have to be mindful. So what is drift? So basically drift is when you train a model, you have it in the system or whatever, and then time goes on, and now the model sucks when it didn't suck before, right? And so why does that happen? It happens for a lot of reasons. It can happen because your population has changed, the setting has changed, technology has changed, a flow sheet value that used to go from 0 to 20 is now 0 to 100 for whatever reason, changes in behavior. Lots of things can happen. We were part of a paper that looked at one of the sepsis epic alerts, right? And as you can imagine, during COVID, the sepsis alert went nuts, right? Because these patients came in, they were super sick, and they didn't have sepsis, but they had a sepsis mimic, right? They had sick COVID. And so the number of alerts goes up, and now we're causing all these workflows to get put into place, like checking lactates and giving antibiotics and telling all of our users to do stuff. And in a lot of hospitals that had the sepsis model in place, they turned it off, right? Or changed the thresholds because the whole population of our inpatient services changed in 2020, right? And so you have to be mindful of that and keep an eye on it. This is another example of how COVID changed a machine learning model, right? So this is a machine learning model that, again, tries to predict if an ED patient is getting admitted. And if you look at specific features or variables of that model, you can see that so many things changed, right? So during COVID, during the pandemic, the number of just ED visits plummeted, right, in the beginning, because everyone was home, no one was doing stuff, and they weren't out in the streets stabbing each other like they usually do. They were like scared to death of COVID and staying home like they should have. But the patients that did come were sick, and they were getting admitted way more than they were otherwise, right? You go from 25, 30% admission rate to 50, 60%, right? The number of times that you're just getting vitals goes up. The age of the patients changed. The number of walk-ins versus ambulance patients changed. The number of patients that came in with traumas dropped, right? That red line in panel F, versus the number of patients with COVID, spiked because COVID was new. So all of these things changes, and when you do that and you watch, just like if you look at the AUC of the model they had in place, they saw the predictive ability of that model fall off because all of those changes, right? And if you're not paying attention and you're not looking at performance on a regular basis, you're going to miss it, and you're going to think that model that had an AUC of 0.85 is still working that way, but it now may not be, right? All right, so there's a bunch of things that you can do, in terms of dashboarding and whatever, to just look at model performance. I'm going to show you some of the stuff that we do. There's dashboards in Epic, certainly, that can do it. We have our own dashboards that we've built in Tableau, where we basically extract a bunch of model predictions and outcomes, and look to see, what's the number of actual predictions made per day. We have so this is a screenshot of one of our things. But one of the important things is like just knowing if a model stopped making predictions, right? Because that just happens sometimes, right? You have a batch job that's making the prediction every 20 minutes, and then someone forgets to move it to production with an update, and now it's stopped. And you have to know that happened, right? And then we do a bunch of kind of post-production monitoring in terms of looking at how many predictions is it making per day, what's the average prediction per day, what's the distribution of the scores, is it different among different demographic subgroups. We do all this stuff, and this is a dashboard that we have that gets updated every night, that we can look at and explore trends. And then on top of that, we have it's hard to remember to go in and look at every dashboard every day, right? So we have a bunch of kind of anomaly detectors as well. So we'll do something like we have a script that runs in the background, and if it looks like the model was making predictions on 80% of the patients, and now the next day it's making it at 20%, it'll send us an email and tell you the difference. And then we also have whenever we do clinical decision support, if we have alerts or BPAs that are based off of predictive models, really for any kind of clinical decision support, we have a little feedback button, and you can press either a smiley face or, more often than not, a frowny face, and give feedback, and they'll just they can write whatever they want. And whenever someone writes something, I get an email about it, right? So this is Alexei, who I know, who said, super cool idea. It's very rare to get positive feedback, to be honest, on alerts, as you guys all know. More often, it's something like this: pop-up is too lengthy, too much data. And we get feedback like this, and we look at it, and we're like, yeah, you're right. We are showing you too much. Let's make this easier to look at, and then we fix it. All right, so how do you measure impact? How am I doing? Oh, I got plenty of time. Cruising. All right, so we put into place an alert in the system, which we just retired, sadly, just a month ago. But basically what it was trying to do was identify patients that were highly likely to get admitted from the emergency department. And as a part of our infection control policy, and probably similar to all the healthcare systems around here, if you were getting admitted to the hospital, you needed to have a COVID test, right? You needed to know what your COVID status was, unless we already knew you were infected or you were recovered. And the reason that's important is because you can't put someone who is at risk for COVID in the same room as someone who is not, right? Because now you've just spread the disease around even more than it's already spreading around. And so it's really important, and especially for hospitals like ours that have a lot of boarding, right? We have no inpatient capacity most days to move patients through the ED quickly. Understanding what kind of bed that they can go to is super important. And being able to say, yes, they're COVID risk, but then we tested them twice, or we did an X-ray, and now they're low risk, and we had this process of removing that risk flag. That opens up a whole set of other beds that patient could go to that they couldn't otherwise go to if they were just, labeled as COVID risk. So essentially what we did is we put in an alert. We said, you are likely to get admitted. We don't see a COVID test. Order a COVID test, right? And so it's using that EPIC predictive model that I talked about, right? It's using machine learning to determine the risk of admission. We added a couple of additional features on top, like, if you're intubated, you're not going to go home for the most part, although I've done that. But we're using machine learning prediction. We're driving something that the end user sees, and then we put this alert into the system. And then what did we find? We found basically we can reduce the amount of time to getting that COVID test by almost an hour, right? And so that means that if that COVID test comes back an hour sooner and it's negative, and we can eliminate that COVID risk off that patient, that's an extra hour that they have, that bed planning has to find additional beds rather when they didn't otherwise. So there we go. And so so on top of that, you can do a lot of things. You can use dashboards. You can say, these are the number of patients, for example, that are admitted to the hospital. These are the ones that have a bed request. And using that machine learning model, you can say to a capacity, someone who's leading the capacity group or capacity huddles will say, we have 23 bed requests, but we also have 15 that are really likely to get admitted based off of this machine learning model. So you just have to think of what the use cases would be. All right, so challenges, make the slide. So that's great. There is actually a different deck that has that slide made, to be honest, but apparently not today. So first challenge, make the slide. Second challenge, so you have to understand what the problem is. You have to be flexible. I think one of the things, in terms of our experience, in the beginning, we had a technical group, and then we had like a leadership group, and literally we were giving the same presentation twice, and it was really cumbersome. And so we just combined everyone together and made that work. You have to have resources to do this. And I think that's a lot of, when we've talked about this before to other people, they've said, that's great. You have developers, you have data scientists, you have the ability to do this. How do people that don't have this do this? And I think that is challenging, for sure, to be frank. But one of the things that you can do is just know enough about it to ask the hard questions and put it back on the EHR that's making the model, or the vendor, to say, okay, you said your AUC is 0.87. What's the precision recall curve look like? And then watch them flounder a bit as they think about how they respond to that, right? But understanding the workflow really well is really important. But there are a lot of models that we've evaluated that we have not put into the system. And so I think one of the big challenges, especially now with ChatGPT and everything else, is really separating the hype from the reality, right? And the reality is a lot of machine learning models out there. Most of them are not externally validated. Most of them are poorly reported. Very few are in the system, and very few of those actually make a difference. And I'm not trying to be a downer. I want this all to work, but we just have to be thoughtful, because this is patient care, right? This is not just something that you're doing at home on the internet, right? This involves decision making, and so we have to be thoughtful about it. All right, that's it. That's all I got. I'm happy to take questions, but thank you so much for your time.
Hello? There you go. It even has an on button. Great presentation. I wanted to get back to that last point you made about having the resources to do this. Yeah. I was a hospital CIO once upon a time, and making the business case to the people who control the budget is hard. Yeah. And one of the things that is very hard is to show, well, here's either the clinical or the financial value of doing this thing, especially before you've done it.
Yeah.
And I'd go to a presentation like this and I'd say, all right, well, how did you make the business case? Or if you had to do it now, how would you make the business case to say this is worth the investment, other than to say, well, I get to come to the Four Points Sheraton and give this presentation on a Thursday morning?
Yeah, I mean, I think it's hard. I think we were lucky because our team that does this owns clinical decision support in general, right? So we own all learning, essentially. And one of the things that we did when we started our team was we knew that we wanted to make data-driven decisions. So we wrote that into our charter, our proposal. And as we've absorbed like the predictive modeling space, like we're using those same resources. But it is hard. I think the way to look at this is that like this is going to be the future, right? Like there is too much data in the system for any like sane doctor or nurse to review and be able to understand. And so there are going to be layers of machine learning that are getting added to these electronic health records to make consumption and review of all of the data easier to do. And there's going to be more predictions that are going to be forward-facing, that are trying to get you to do the right thing. And there is probably at some point going to be ROI there in terms of like, we're saving money by doing this. And that money is something that we should invest into making sure that we do more of this thing that is going to save more money and cause that cycle. But I think you just have to, I think you just have to make the case that if you want to be able to do this well, you have to invest some amount of resources in it. And it may not, you don't need we have 2 data scientists and we've spent a lot of time doing this, but everything that we've done in terms of like how to evaluate models, we've made available, right? We have code that's up on like the Epic user web. There's a lot of stuff out there that you can borrow and frankly steal from, and so that you can do this reasonably well on your own. Like the software we use is it's free, right? So like you don't need to invest in a lot of technical stuff to be able to do this, but you do need someone that can do a little bit of coding and understands some statistics and does that kind of thing. And we're privileged, right? At Mass General Brigham, we have a lot of resources to do this kind of thing that certainly may not be true for other places.
So one follow-up question, which is, have you done measurements that the executives who write the checks consider meaningful, like the 52 minutes sooner to test for COVID? All right, that's great, but what's that worth, either clinically or operationally or financially?
Yeah.
Have you baked that into your process, and if so, how's that gone? And so on?
We are trying to, but it is hard. Like I've said, like there are very few models that you can really demonstrate clinical impact for, right? And if you do, how do you turn that 52 minutes of lead time to getting a COVID test into a dollar amount that says this is your number of bed hours saved, right? Getting that COVID test sooner doesn't matter if your hospital is at 100% capacity and that person has nowhere to go anyways. It only matters if there is some degree of flexible capacity, and that's a very hard thing to measure on a day-to-day basis, right? So I think it's challenging, but I think that's like the work that we need to do, is to be able to demonstrate the return on investment.
Thank you.
I think I've successfully dodged most of your questions.
I think you have too.
Thanks for your presentation. I think it's great. I am going to run the mic, but I do have a question for you.
Sure.
Because I hear this all of the time. I'm a consumer of some of these predictive models, sepsis bundles, et cetera.
Yeah.
And so I hear from end user nursing in particular that there's a concern that critical thinking skills may be diminished as time goes on, because we're just going to have more and more AI and predictive models coming. So from a clinical decision support perspective, how are you looking at balancing that? Because to me, it should be a tool as an adjunct to your critical thinking. So whether it is that you show somebody, this is how we came up with the score, or something else.
So I think that's an important question, and I think that's an important comment, right? That like, if we're doing all this, if the system is doing all this stuff for you, then how are you ever going to learn yourself? I think that is a problem, but I don't think it's as much of a problem now that it will be in 10 years. I think that problem is going to get worse as models get better, right? I think on top of that, there is just so much data out there on even one specific patient that the amount of time it would take to read through, the last 3 months worth of notes or 6 months worth of notes to really get like the complete comprehensive picture of a patient and look at like what their blood pressure trend has been over the last 3 years or what their hemoglobin A1C is, it's like too much, right? Like it's not possible within the time constraints of like modern medicine. If you have a 15-minute PCP appointment, there's no way that they can do that, right? They can try, but they just can't. And so these layers of like, we're gonna promote something that you want to see based on what we think is important for you to see is going to be the next step, right? It's going to be like having a large language model look at your cardiac history in your entire record and summarize it in a paragraph so that you don't have to go to 15 places to find it. That's what it's going to be. I think there's more benefit there, honestly, than us trying to say, you should do this or you should do that. But it's a challenge for sure, and I think it's going to get worse as things go on. But I can also tell you, as like the lead for our clinical decision support team, like we show alerts to our users all the time saying, you're trying to do this, that's a bad idea, you should do that. And like most of the time they're just like, I don't care what you just said, right? And they just ignore it because they want to do what they think they're going to do, and sometimes they're going to be right and sometimes they're going to be wrong, but it's a problem. Dodge that one too.
Hi, thank you. I'm Tanya Hunksmeyer. That was a fantastic presentation.
Oh,
I'd like you to speak to how you do the education in more detail to deal with these issues, such as adoption, and to what extent. I loved the model where you're putting the information before they think about making the decision, because I think reactive decision support just doesn't work very well at all, as you know.
Right.
So I'd like to understand better how you approach the education regarding adoption and risk mitigation, because complacency is a challenge, and also just ignoring the data is a challenge. But and in terms of safe, effective use of this kind of approach and this information. Thank you.
So do you mean education of users or education of our governance group?
Both,
Okay.
because governance, I think, it needs to, what you just went through was so effective at helping potentially a governance and clinical users really understand how this data works. But attention span is hard. Getting attention of users is difficult. So
I think on the governance side, it's a bit easier because there are probably half machine learning people that know this stuff kind of probably better than I do, for sure. And then there's the clinicians that are getting exposed to it month after month after we have these meetings, right? So I think that part is easier, in terms of like how to do good model evaluation. And papers are getting better too in terms of these external validation papers like the one I showed or countless other ones that have been coming out recently. Education of users is a much different thing. And it is very hard because one of the things I didn't have, and probably should have been a challenge on that slide I didn't make, was that there is a difference between different kinds of predictive models, right? If you have a logistic regression model or a linear regression model or an explainable regression model, you can say this value on this variable contributes this much to this prediction. If you have a neural network, you can't do that, right? And for most machine learning models that are any more sophisticated than a regression model, you cannot say for this prediction, this is how much the weight was for this feature. It's just not possible. And there's like, a mountain of linear algebra that's happening behind the scenes, and it's not that explainable, right? And so our approach has been the user at the time when they're managing sepsis in the ICU, they don't care about your model weights for, how much, your, RDW affected your ability to have sepsis. Like, they don't care, right? They just want to know the main thing, that like they're at risk for this. We typically will put in like a positive predictive value, right, at that threshold that we chose, and say, you know, at this score, they have this % chance of developing this bad thing, and like that's it. We've tried, like I showed you with that feedback, right? We've tried showing a table of the features and the feature weights, and it's just like too much, right? Because like they don't have time, they don't care enough.
Is your legal department asking you to put any disclaimers in the explanation, or it's just an interesting?
No.
There's all this FDA stuff coming down the.
Yeah, we haven't done that. I think in general, we're approaching this like any other kind of clinical decision support, that like we will do our best to prompt you with the right thing, and sometimes we're going to be wrong, right? And it's your decision to take our advice or not, right? There's nothing that we do, certainly, in the predictive modeling space that says, if this happens, this will always happen. That's not how we operate, because the models typically are not good enough to do that.
Thank you so much for a great presentation.
Awesome, thanks guys.